Okay, so hi everyone. So today's speaker is George Mountrichas, who will talk us about the coevolution of AGN and their host galaxies. But before, let me introduce George a little bit. So George is graduated with a degree in physics from the University of Patras. And then he moved to England, where he obtained first a master in astrophysics at the Queen Mary University of London. And then he obtained the PhD from the Durham University in 2008. After the PhD, George went to the military service, and he had a career break in total of for a total of 3 years. Then he went back to research with a postdoctoral position at the Institute of Astronomy and Astrophysics at the National Observatory in Athens from 2011 to 2019. And then since November of 2019, he is a postdoc at the Instituto de Física de Cantabria in Santander, Spain. So let me... Okay, so without any further ado, I think the floor is yours, George.
Thank you, and thank you for inviting me to give this talk today. So in this talk, I will discuss the coevolution of AGN and their host galaxies, and I will present you some of the results that of our work on this topic. And this work has been done in collaboration with people that you see. Where's the cursor? Can you see cursor? No, is it? I cannot show my... Anyway.
Yes, we can see.
I cannot find my cursor. Okay, I found it. Okay, sorry. So in collaboration with the people that you see here, the main collaborator in this work, my main collaborator is Veronique Bois, but also the rest of the SIGAL team. SIGAL is an SD fitting code, and these people here have contributed to the development of this code. And also, a part of this work has been done in collaboration with Francesco Sankar. So, many studies in the last decades have shown that there is coevolution between galaxies and their supermassive black hole in their centers. And this coevolution has been demonstrated by, for example, correlations that have been found between the supermassive black hole mass and various galaxy properties, such as the bulge or stellar mass. But perhaps the tightest of these correlations is the one between the supermassive black hole mass and the stellar velocity dispersion. And an example of this correlation is shown in this plot here, taken by the famous paper of Ferrares and Merritt 2000. We also know that both phenomena, both the black hole growth and the star formation, are driven by are fueled by the same material, which is called gas. And also both the AGN activity and the star formation peak at similar cosmic times at around redshift of 2. So for instance, on the left plot, we see this is a figure from Sobral et al. 2013, where they have plotted the stellar mass density as a function of the age of the universe. And it shows that the stellar mass density peaks at around 4 gigayears, which roughly corresponds to redshift of a bit less than 2. And similarly for QSOs on the right plot, where the right plot shows the number of QSOs per redshift from the paper of Boll et al. 2000 using the 2QZ survey. And again, we see that the number of QSOs peak at around redshift 2 and then drops as we move to lower redshifts. So okay, there are many ways, many methods that one can apply in order to study this interplay between the activity of the supermassive black hole and their host galaxies. But at least most of these methods, what they do is to examine possible correlations between important galaxy properties, such as the star formation rate and the stellar mass, and examining possible, as I said, correlations of these properties with important supermassive black hole properties like the black hole mass and the X-ray luminosity, which is a proxy of the agent power. So in the next slides, I will present you the methods that we have applied in order to study this symbiosis, this interplay between the supermassive black hole and the host galaxies. So the first of these methods that we used was presented in a paper earlier this year in collaboration with Francesco Sanca. And basically what the goal of this work was to see how the star formation rate and the X-ray luminosity evolve during the lifetime of the galaxy. And by that, I mean how these two properties vary as the galaxy moves from one galaxy phase to the other, from the star forming to the starburst to the quiescent phase. And then we compared the observational results, our observational results, with predictions from theoretical models. So in order to do that, we used about 5,500 X-ray HCN from 4 fields: the cosmos, the Bootis, the XMM-XXL, and the IFEDS field that has recent observations from the Rosetta satellite. Our samples span a wider redshift of range from 0.5 to 2.5 and about 3 orders of magnitude in X-ray luminosity. So we then classified our sources into star-forming, starburst, and quiescent using the specific star formation rate values. And here in this table, you can see the number of sources we have for each galaxy class and how these numbers are distributed in the various redshift bins that we used in our analysis. So one of the things that we studied is the X-ray luminosity for different galaxy phases with constant stellar mass. So these plots here present the LX, the X-ray luminosity versus stellar mass. Different panels correspond to different redshift intervals, as indicated on the top of each panel, and different colors and symbols to different galaxy phases. So we have green for star forming, blue for starburst, and red for quiescent systems. So one of the things that we can see from these plots is that in all cases, in all redshift intervals, starburst galaxies present the highest X-ray luminosities compared to star forming and quiescent for the same stellar mass, whereas quiescent show the lowest X-ray luminosities. This result, in combination with the well-known main sequence, I mean the relation between the star formation versus stellar mass, indicates that there is a gradual extortion of the gas that fuels both the supermassive black hole and the star formation rate. We also noticed that there is a mild increase of the X-ray luminosity as a function of stellar mass, which is more evident at high redshifts, higher than 1.5, and then there is a gradual flattening as we move to intermediate and lower redshifts. Now, this increase is probably driven by the underlying black hole mass stellar mass relation, and this gradual flattening, if we assume that the ratio of the black hole mass over stellar mass is constant at all redshifts, as most studies have found, then this gradual flattening can be explained by a decrease of the mean Eddington ratio. Then one more thing that we studied in this paper is to see how the X-ray luminosity and the star formation vary as during the lifetime of the galaxy. And by that I mean, as I said, during different galaxy phases. So these panels show results for a specific stellar mass bin from 10.5 to 11, but we found similar results for all sources with stellar masses from 10 to the 12. So what we have done here, and again, different colors correspond to different galaxy phases. Again, green for star forming, blue for starburst, and red for quiescent in all panels, and also different symbols correspond to different redshift intervals, but there is no dependence of our results with redshift. And so what we have done is we first studied how the ratio of the X-ray luminosity over SFR varies for different phases, and we compare that with the predictions of merger models, and these predictions are shown by the solid line here. And specifically, these models here are those that were presented in Di Matteo et al. 2005, and they are the same with Hopkins 2012, etc. So basically, these merger models assume that the galaxy starts its lifetime in a star-forming state, and then a merger occurs, and there's gas that is funneled to the system, and about 1 gigayear later, the galaxy, because of that, enters the stardust phase, and about 0.5 gigayears later, according to these models, the gas has been depleted, and the galaxy enters the quiescent phase. So what observations showed is that the ratio of the X-ray luminosity over SFR drops when the galaxy enters the stardust phase, and this drop is not predicted by the models, but it has also been found in other similar studies, for example, the Rodriguez 2015 paper. And then the ratio increases by a factor of 1.5 dex in the quiescent phase, and this is in line with the predictions of the models. Now, in order to see what drives these variations of the LX over SFR ratio, if it is the star formation rate of the X-ray luminosity, in the next two panels, we examined how these two properties vary with time. And we normalize in both cases their values with the value they have in the star forming main sequence. So regarding the star formation rate, what we see is that, as it is expected, the star formation rate increases in the stardust phase, and then it drops in the quiescent phase. But this increase is in line with the predictions of the models. We also saw here the same results, but in this case we used non-AGN systems. So galaxies that do not host an active supermassive black hole. And these are shown by the open symbols connected by the dashed lines. And we see that the variation of the SFR from one galaxy phase to the other is similar regarding of the activity of the supermassive black hole. That is, I mean, regardless of whether we have an AGN or a non-AGN system. Regarding now the X-ray luminosity and how it varies during time, we see that observations show that the X-ray luminosity increased by a factor of 2 or 3 in the stardust phase, and then it drops in the quiescent phase by a similar amount. But in this case, these results are not in line with the predictions of the merger models, since the merger models predict a much higher increase of the X-ray luminosity by a factor of at least 70, if not more, of the X-ray luminosity in the stardust phase. Now, what these results could mean, for example, the fact that the star formation rate, the variation of the star formation rate from one galaxy phase to the other is similar for AGN and non-AGN, could imply that the AGN feedback does not play an important role in the variation of the SFR. An alternative scenario, though, could be that because of the time lag that exists between the triggering of the two phenomena, and also the different lifetimes of the star formation and the aging activity, perhaps could wash out any causal links between the star formation and the X-ray luminosity. And if we assume that the latter is the case, that, I mean, the aging feedback does affect the star formation rate, and we cannot see it because of what I said, the reasons that I mentioned, then one should assume that this aging feedback is very efficient, because in the stardust phase, the X-ray luminosity increases only by a factor of 2 or 3, whereas the star formation rate increases by a factor of 7 or even more. even up to 10. So these were the main results of this work, where, as I said, we tried to see how the X-ray luminosity, the main goal was to see how the X-ray luminosity and the star formation rate varies during the lifetime of a galaxy, and also compare it with this variation with non-AGN systems. Now, another popular method that is used in studies to examine the interplay between the AGN feedback and the host galaxy is to study the star formation rate as a function of the X-ray luminosity, since the X-ray luminosity, as I mentioned, is a proxy of the AGN power. Now, the first studies that followed this approach found controversial results. Some found a positive correlation between the SFR and the X-ray luminosity. Others found a flat correlation, or a correlation that is different based on the LX regime. And these controversial results were attributed to the cosmic variance and low number statistics, basically to the small sizes of the X-ray samples that were available more than a decade ago. Although, to be honest, this was also the case even when larger samples were used more recently. But in any case, I'm not going to go into the details of that, because instead of doing that, instead of studying the SFR versus the X-ray luminosity, more information can be gained regarding whether there is an effect, whether the AGN feedback affects the star formation rate of the host galaxy, if instead we compare the star formation rate of AGN with the star formation rate of non-AGN, of main sequence star-forming galaxies with similar redshift and stellar mass. And most works that have followed this approach, they calculate what is often called normalized SFR. So the normalized SFR is what I mentioned just now, means the ratio of the star formation rate of AGN to the star formation rate of star-forming main sequence galaxies with similar redshift and stellar mass. So I should say here, though, that most studies that have followed this approach, especially those that have examined this correlation at high redshift, higher than 1, they have used analytical expressions from the literature in order to calculate the star formation rate of non-AGN systems. And these analytical expressions, for example, the Schreiber 2015 equation, which is the most commonly used equation in these cases, basically gives the star formation rate of main sequence galaxies given the redshift and the stellar mass of the source. Although this is a necessity, to use these analytical expressions from the literature to calculate the star formation rate of star-forming galaxies, and then use something different, for example, SED fitting, to estimate the SFR and the stellar mass of X-ray datasets. Although it's a necessity because of the scarcity of galaxies at high redshifts, this approach may hint at systematics that can affect the overall results and conclusions. And in order to illustrate this, here in the two left panels, I have plotted the distribution of the difference of the star formation rate calculations using the SIGAL code, which, as I said, is an SED fitting code, with the star formation rate using the Schreiber equation, which I showed in the previous slide. So different colors correspond to different redshift intervals. And as we can see, the two calculations agree well at high redshifts, since the difference of the distribution of the difference peaks at close to 0. But then as we move to lower redshifts, we see that SIGAL tends to calculate lower SFR values compared to the analytical expression of Schreiber. And the bottom panel shows the results from a similar exercise, but in this case, we have used an analytical expression from Schreiber, from Whittaker 2014 instead of the Schreiber expression. And in this case, we see that the two calculations agree well at low redshifts, but again, there are systematic offsets at intermediate and higher redshifts. So this was just an example to illustrate, to show you, these systematics that can be introduced in when one estimates, calculates the normalized transformation rate using this approach. And also, apart from this, there are also differences in different studies of how sources are selected, different photometric selection criteria. And even if someone uses the same method to calculate the host galaxy properties, such as the star formation and the stellar mass, using different SD fitting algorithms, or even the same algorithm, using different modules to model the star formation history, to model the AGN emission, etc., and different parametric grid, all these can introduce systematics. So on the right panels, I saw the normalized star formation rate, which I defined earlier as a function of the X-ray luminosity. Different colors correspond to different redshift intervals, and the black field circles show the average values. But basically, what I wanted to show with this plot is that in the bottom panel, we have used these are data from the Bootis field. So in the bottom panel, we have used the analytical expression of Schreiber to calculate the star formation rate of star-forming galaxies, and we see that we get a linear relation of the SFR norm with X-ray luminosity. But on the top panel, instead, we have compiled our own galaxy control sample using the same photometric selection criteria, the same mass completeness limits, the same method to calculate galaxy properties, and that is the SIGAL code with the same modules and parametric grid. And in this case, we see that the field circles have the SFR norm measurements versus the X-ray luminosity, so a different behavior. So it is important, although as I said, in some cases it is a necessity to use analytical expressions, but it is important to keep that in mind. So what we did in some recent papers of ours is that we examined this SFR norm LX relation in using data from three fields: the Cosmos, the Bootis, and the Ifeds field. And we have also split our measurements in different stellar mass bins. So what we found is that, I should also say that this dashed line here, based on the definition of the SFR norm, basically indicates that this is where the AGN have similar star formation rate with non-AGN systems, that is with star-forming main sequence galaxies. So we see that for the least massive and for the most massive of our systems, with stellar masses from 10 to 10.5 and from 11.5 to 12, we find a flat relation between the two properties, between the SFR norm and the X-ray luminosity, and also that we see that the SFR norm values are consistent with 1, which means that for this system, AGN and non-AGN have similar star formation rate. However, for intermediate stellar masses, from 10.5 to 11, shown in this top right panel, and from 11 to 11.5, shown by the bottom left panel, we see that at high luminosities, higher than 10 to the 44, consistently we find SFR norm values higher than 1, which means that the star formation rate of AGN is enhanced, not by much, by approximately 30% compared to non-AGN systems. However, for AGN with low to moderate X-ray luminosities, so lower than 10 to the 44, we see that the vast majority of the beams in all these two stellar mass for sources in these two stellar mass ranges, they are lower than SFR norm, but statistically, let's say, consistent with one, which means that for these systems, in these systems, the HGN tend to have lower or at most equal star formation rate with non-HGN systems. So basically, what we wanted to do next was to compare, to investigate basically this part a bit more. So we thought to study the star formation histories of HGN with low to moderate X-ray luminosities and compare the stellar populations with the stellar populations of non-HGN systems. So in order to do that, we cross-matched our data set in the Cosmos field, our data sets, both HGN and non-HGN data sets in the Cosmos field with the legacy catalog. So the legacy catalog has observations, has basically spectral measurements for spectral indices for a bit less than 4,000 galaxies in the ultravista region of the cosmos. And there are two available spectral indices measurements in this catalog, in the legacy catalog, that are useful for what we wanted to do. The first one is the calcium break, the DN4000 index, which has been used in the past as a proxy of the stellar age of galaxies. So basically, small values for this index mean that the galaxy has a young stellar population, whereas large values of DN4000 means that the galaxy has an older stellar population. And the other spectral line that has measurements in the legacy catalog, and it is useful for studying the star formation, the star populations of our sources, is the H delta Barnell line, which again, I mean, high values of this spectral line indicate that the system has undergone a recent star formation burst, whereas low values means that the system has not undergone a recent burst. So we cross-match our data sets in the Cosmos field with the legacy catalog, and we ended up with 69 X-ray HGN and a bit more than 2,000 non-HGN systems that span the redshift range from 0.6 to 1.3. This is the redshift range that's covered by the legacy catalog. Okay, now before moving to the actual results, one more thing that we did in this paper is that we wanted to see if the inclusion of these two spectral indices, if it would allow SIGAL to better constrain some star formation history parameters, because it is known that star formation history parameters are highly degenerate, and therefore it's very difficult not only for SIGAL, but for any SD-fitting algorithm to reliably constrain them. So in these plots, what is presented is the mass-weighted stellar age on the y-axis and the age of the universe at the redshift of the source on the x-axis. The black lines correspond to the measurements when we do not include these two spectral indices in the SD-fitting process, and the blue contours are the measurements when we include the two lines. So what we can see here is we see that when the two lines are not included in the SD-fitting process, then SIGAL tends to assign values close to 3,000 regarding the stellar mass. And basically, this is the lowest value allowed by the parametric grid that we used for the SD-fitting. However, when the two lines are included, then we see that the distribution of the values that SIGAL assigns for the spectral age is it's much flatter, and it is better the age of the universe at the redshift of the source, basically the redshift of the sources. So these results are on the left panel for galaxies, on the right are for the AGN, but they're similar. The results are very similar, and the same conclusions are drawn. So basically, we see that including these two lines allows Seagal to better constrain the edges of the stellar populations, both in the case of galaxies and in the case of AGN. Now, regarding what is the effect of including these two lines regarding the measurements, the Seagal measurements for important galaxy properties, such as the star formation rate on the left panel and the stellar mass on the right panel, we do not find any differences regarding the SFR calculations of Seagal with or without these two spectral indices. But regarding the stellar mass, we see that there is an offset by approximately 0.2 dex in these calculations when the lines are included in the ST fitting process. Okay, now so moving now to the actual, to the main results of this work. So, as I said, our goal was to study the stellar populations of star-forming galaxies, compare the stellar populations with the stellar populations of low to moderate LXAGN. So here is the H delta and the TN4000 plot and the distribution of galaxies with the blue contours and AGN with the red circles in this space. And what we see, so blue lines are for distributions of galaxies and red for AGN, and these distributions are weighted based on the different stellar masses of the two populations. We see that AGN tend to have higher TN4000 values, which means that they tend to have older stars compared to non-AGN. And also regarding the H delta distribution, we see that AGN prefer intermediate values for this spectral line. So basically, they do not prefer systems that have undergone a recent burst. In both cases, we see that the galaxies have a nearly double peak distribution, both for H delta and the TN4000, and we will see in the next slide where these two peaks come from. So this result is in agreement with what I showed earlier when I was presenting the normalized SFRs of fraction of X-ray luminosity, in the sense that in that result we found that the star formation rate of AGN is somewhat lower compared to the star formation rate of non-AGN systems, which is compatible, it's in agreement with the fact that they have AGN have older stars and living systems that have not undergone a recent burst. We also then checked what is the effect of morphology for the two populations, for AGN and non-AGN. And for that reason, we cross-matched our sources with the catalog, the catalog of Lee et al. 2021, where they have used deep learning methods to classify the sources into bulge-dominated and non-bulge-dominated systems. So bulge-dominated are systems that they do not have these like features or irregularities. In any case, solid lines present the distributions for galaxies and dust lines for AGN. And what we see is that non-bulge-dominated galaxies have significantly lower TN4000 values, so significantly younger stars compared to bulge-dominated galaxies. And this is also the case in the case of AGN, but we see that the differences is much smaller for AGN regarding the stellar populations of bulge-dominated and non-bulge-dominated systems compared to the differences we see for galaxies. So morphology seems to play a more important role in the stellar population of non-AGN systems compared to AGN. Okay, now I think it's been like 35 minutes. Basically, this is what I had in mind to present for this talk. And I mean, the next slide is the summary of what I just presented. But I was thinking, I mean, I don't know, it's up to you. I am working now on a paper that is related to this, to the work that I just presented. It's a paper that we hopefully submit next month. So I don't know if you would like to also show you some of these preliminary results we have, or maybe I should, I mean, you know, finish with a summary, discuss with that, what I have presented, and if there is time at the end, maybe I could show you these preliminary results from the project that I'm working now.
I think Yorgos, we still have time. So if you want to present us some new result, I think you can do it.
Okay.
Up to you.
Then okay. So just to complete this part of the talk. So this is the summary of the what I presented up to now. So we found that the variation of the SFR as the galaxy moves from one galaxy phase to the other is consistent with the predictions of merger models, but the fluctuation of the X-ray luminosity is significantly lower compared to these predictions, to these theoretical predictions. We also found that the star formation rate, the variation of the star formation rate from one galaxy phase to the other is similar basically for both HGN and non-HGN systems. So it appears to be independent of the star formation history of the supermassive black hole activity. Studying the normalized SFR as a function of the X-ray luminosity, the main conclusions from this part of our work was that galaxies that host luminous HGN a few times with X-ray luminosity a few times higher than 10 to the 44, we found that they have enhanced by approximately 30% star formation rate compared to non-HGN systems to start forming galaxies with stellar masses from 10.5 to 11.5. Whereas X-ray HGN with lower X-ray luminosities, lower than 10 to the 44, tend to have a lower or at most equal star formation rate with that of main sequence galaxies. Again, this conclusion holds for this specific stellar mass regime from 10.5 to 11.5. Now, for the least massive and the most massive of the sources in our data sets, these show a flat SFR norm-LX relation with a value of approximately 1, which implies that HGN and star-forming galaxies have similar star formation rates for these stellar masses. We also found that low to moderate X-ray luminosity tend to live in galaxies with older stars and that have not undergone a recent star formation burst compared to non-HGN systems. And also we found that morphology plays a more important role in the stellar population of non-HGN systems, whereas it does not seem to affect significantly the stellar populations of HGN, or at least low to moderate X-ray luminosity HGN. Okay, and then regarding the project that I'm currently working on, so the idea was to, I mean, there have been many studies and also some very recent studies that have examined the star formation rate of galaxies as a function of the cosmic environment. So the star formation rate of galaxies, they compare the star formation rate of galaxies in fields, in filaments, or in groups and clusters. However, at least to my knowledge, they do not take into account these studies the effect of the HGN feedback. So whether this finding could change for systems that host HGN. So in order to do that, we used our data sets in the Cosmos field and the public catalog from Darvis et al. 2015 and 2017, where they have calculated the density fields in the cosmos field, and then they have associated sources in filaments, in fields, filaments, and clusters. So in this plot, I presented normalized SFR as a function of the X-ray luminosity for the different cosmic environments, and green is for the sources for isolated sources in the field, and blue is for sources associated with filaments, and red for sources associated with clusters. So one thing that we can see is that consistently the SFR norm increases as we move to more denser environments. And another thing that one can notice is that for the sources that are in the field, in the least dense environments, the SFR norm LX relation is flat. Whereas in more dense environments, the SFR norm increases for moderate LX-HGN. And by moderate, I mean with for HGN with X-ray luminosity higher than 10 to the 43. And this perhaps can be seen clearly here, where we have used the overdensity values estimated by this Darvis method for each source, and we have split it. We have selected sources that belong to the 20% highest, that have the 20% highest overdensity values, and this is what is called a high density field, sources in high density fields, and also the 20% sources that have belong to the 20% lowest overdensity values, classified as low density fields. And again, we see what the previous slide was showing, but perhaps here is more statistically significant. So again, there is a flat SFR norm LX relation, and it is also below the dashed line, which, as I mentioned in a previous slide, this is the line that indicates when the star formation rate of HGN is similar to the star formation rate of non-HGN. So the relation is flat, and this shows that the HGN have in low density environments have lower SFR compared to non-HGN systems. Whereas in the most dense environments, we see that above 10 X-ray luminosity 10 to the 43, we see an increase of the SFR norm, and the SFR norm values are higher for the highest density fields compared to the lowest density fields. We also cross-match this catalog in a similar manner as we did before with the legacy catalog to study the stellar populations of the systems. So this is, similar to a recent paper by Sobral et al. 2012, although in this case, in this paper, they only study galaxies, whereas here we also, as I said, we see what is the effect of the HGN. So what we see is that regarding, so again, the two spectral indices that I mentioned earlier, the DN4000 and the H delta values. So the bottom row of this table show the results for galaxies in the field, in the filament, in filaments, and in clusters. And what we see is that the DN4000 increases as we move to denser environments, and the H delta decreases. So this means that the stellar population of galaxies is older in denser fields. Regarding the HGN, prompted by the previous results that I showed in the previous slide, we split them into low luminosity and moderate luminosity sources. And what we see is that for low LX HGN, both spectral indices have similar values regardless of the cosmic environment. Whereas in the case of modern luminosity AGN, based on the values of these two spectral indices, AGN seem to have younger stellar populations in more dense environments. And here in this table, in the bottom table, we have split the sources into star forming and quiescent using the specific star formation rate values, and we examine again the values of these two spectral indices for different density fields. Because of the small number of X-ray AGN that we have available, we do not split here in this example sources AGN based on the luminosity. But in any case, what we see is that star-forming systems, both in the case of AGN and in the case of galaxies, have similar stellar populations regardless of the density field, whereas quiescent systems seem to have significantly older populations in dense environments compared to less dense environments. So it seems that the variations that we saw in the top table are mainly driven by the quiescent systems. And finally, we also studied the morphology. So we split again our sources based on the cosmic environment, but we also split them based on the morphology, where they are bulge-dominated and non-bulge-dominated systems. And one thing that we see is that both AGN and galaxies have the same fraction of both populations live in fields. For example, 32% of AGN live in fields compared to 41% for galaxies. 57% of AGN, 57% live in filaments compared to 53% for galaxies, and again similar fraction for clusters. So regardless of the supermassive black hole activity, regardless of whether the system is host and AGN or not, the same fraction of galaxies is associated with different cosmic environments. We also find that the same fraction of bulge-dominated systems is found both for AGN and non-AGN, which is approximately 25%. But one important, perhaps, difference is that the fraction of bulge-dominated systems in the case of galaxies increases from 19% up to 28% as we move to denser environments. Whereas on the other, for AGN, we see that the fraction of bulge-dominated systems significantly drops as we move to denser environments. Now, what these results could imply or suggest is one possible interpretation is that perhaps the AGN feedback in dense environments counteracts the removal of the gas and prevents the quenching. And the higher the AGN activity, and by that I mean the X-ray luminosity, the more efficient the AGN feedback is. And this is why we see increased NCFR norm values for modern luminosity AGN. An alternative and probably most possible scenario is that perhaps there is a common mechanism, a merger, that triggers both phenomena, both the AGN and the star formation. And the more gas that is shown to the galaxy, the higher the star formation and the AGN power. And maybe to this scenario corroborates the fact that we found that bulge-dominated AGN are scarce in dense environment. Now, regarding the lower star formation rates that we found for AGN compared to non-AGN systems in low density fields, I'm talking about isolated sources. This could be due to the low availability of gas, since there have been theoretical models, simulations, that say that when the gas is in when the galaxy is in a gas-cooled phase, then the agent feedback would suppress the star formation rate. And thank you. This is basically what I have prepared to present today.
Thank you very much, George. Now it's time for questions. So you can unmute yourself or raise the hand as you wish. I see one raise hand, Felix.
I think Felix was clapping.
Yes, I'm sorry.
Then I see two more. Thank you.
Andreas was first.
Andreas.
Okay, thank you, Giorgio, for the interesting results. I was wondering, actually, I have two questions. One is a very basic question because I missed the very beginning of your talk. So the objects that you showed that have luminosities, very high luminosities, 10 to the 42, 10 to the 43, these are AGN or star-forming? Because in some of the plots in the beginning, they were listed as star-forming galaxies.
Which plots? Well, I don't know which plot.
From your 2023 paper.
Okay, from the 2023. So, for example, here you mean?
Exactly, yeah.
So no, these are okay. So I see what you mean. So these are X-ray detected AGN, which live in star-forming systems. So basically, okay, in all of these studies, we assume that if a system has an X-ray luminosity which is higher than 10 to the 42, that this system is an AGN. Because at lower
so you use the standard convention then. Okay.
Yeah, exactly. So because at lower X-ray luminosities, you may have contamination. The X-ray emission may come from not the supermassive black hole, but from other sources within the galaxy. But so yeah, this is how we let's say we select AGN, those sources that have LX higher than 10 to the 42.
Okay. And I have one more question regarding your last result regarding the lack of AGN in bolts-dominated systems in dense environments, if I understood it right.
Mm-hmm.
I find this a bit counterintuitive in the sense that generally in dense environments, we have more early type galaxies, more bolts-dominated systems. So I'm wondering why this is happening.
Well,
why?
There are two things. I mean, this is true for galaxies. I mean, for galaxies, and when I say galaxies in general, in all this analysis, what we have done is we have excluded from the galaxy samples that we have compiled sources that are X-ray detected and are included in our AGN sample, of course, and also sources that have a significant, AGN fraction in Seagal. I know you are familiar with Seagal, so I don't explain this more. Okay, so for these systems, there is indeed an increase of bulk-dominated systems in clusters. Now, why we don't find them regarding the AGN? Okay, one thing is that a common problem with X-ray studies is the size of the sample. You always start with a large sample, and then you end up with a significantly smaller one because of the various cuts, etc., etc. So here, this is why I present here the number of sources that we have. So there are only 4 sources, basically 4 AGN that belong to a cluster, and because of that, I also used the density values from this Darwin's method that are available in order to select sources in high dense environment and low dense environment, and the goal was basically to increase, the number of AGN that we have in dense environments. But again, even by doing that, we have 13 AGN. So what I say in the paper is that, okay, these are some indications, but to be honest, larger samples are required. And my idea is basically to apply something similar using the eROSITA sources now, both in order to increase the number of sources that we have available to the size of the data sets, but also to increase the luminosity baseline to even higher, luminosities. So perhaps, if we say that it is indeed the case, if this result is true, then my understanding from this analysis, and these are preliminary results, and I'm open to suggestions, is that basically AGN are in dense environments are results of mergers, and this is based also from the values of H delta and from the results we found of the increased SFR compared to non-AGN systems in similar dense environments. So probably these are sources, with interactions with other galaxies, mergers, etc. And this is why they do not show up as bulge-dominated systems.
Have you looked for radio signatures? Because some of those AGN in the bulge-dominated systems might be sort of quiescent AGN that are like more radio loud than optical or X-ray loud. And this may have to do with the fueling of the AGN. So there might be like the hot phase fueled AGN versus the cold phase fueled AGN that you would see in the non-bulge dominated systems.
Okay, that's a good idea. No, I haven't done that, but okay, I will. I'm making a note now. I'll see. I don't know if what data are available, but I will have a look at it and and try to see. Yeah.
Okay, Andreas, do you have any other question? No, you're done.
Let somebody else speak and then.
Okay, because I see your hand is still rising. Vasilis, no?
Yeah, I lowered my hand by maybe it was already discussed. Yorgo, how do you actually, I was wondering whether this difference that you see in the bulge dominated systems may be simply because of the fact that once the bulge is being visible, right, or able to identify it, then you don't have that much gas which could actually fuel the central supermassive black hole and bring the galaxy about the characterization for AGN dominated system. Do you think that this could be one of the reasons why?
Basically, but the thing is that, if I understand well, you're saying that basically when a galaxy appears as a bulge dominated system, there's not enough fuel to probably trigger the AGN. But the thing is that, we have found in this preliminary paper, but also in the previous paper from which I presented results, we found the same number of bulge-dominated systems, both in the case of AGN and non-AGN. In this specific sample, the fraction is 25%. If I remember correctly, in our previous paper, it was 30%. So, both populations, both AGN and non-AGN, appear to have a very similar fraction of bulge-dominated systems. So to me, the question was, since they have the same fraction, why this fraction, the trends that this fraction follows is different for different cosmic environments.
Okay. Yeah, thank you.
Okay, any other question? Okay, if not, then let's thanks George again. Thank you very much.
Thank you for the invitation.
So I will stop the recording now.
Yeah.